Okay, so let me share my screen with you. And like we always do, based on our program schedule, we've at least covered deep neural networks, and then we've dealt with some model development using neural networks. And then we looked at instances where we can deploy our model to some real world applications like web applications. And we've seen a few things over here. Like I said, I forgot to share the link to the other video I spoke about the last time, but I believe if you follow through with what we did with Streamlit, you'll be able to navigate your way through. It's a very simple, I mean, you can get a very simple interface and then you work with it. Now, today we are going to continue our journey with deep neural networks. And today we are going to look at a special kind or type we refer to as the convolutional neural network. So I believe the term convolution, okay, is more or less the root word or something which is a little bit new, because as far as neural networks are concerned, we've heard that over and over again. So if I'm to do a Google search on the word convolution to actually get a sense of what that word actually means, it basically says a convolution is a mathematical way of combining two signals to form a third signal. At least that's from an engineering point of view. So we get that. I just wanted to find maybe if there's a simple grammatical meaning, but then all that we are seeing is that, especially those of us who are quite familiar with digital signal processing, you deal with some of these things. But then um, the lessons we are trying to, or the inspiration we are getting from this signal processing bias definition is the fact that we are combining two or more things. So things are being convoluted one way or the other. Now, what I'll do is because we don't have much time, okay, and then at least we have that general understanding of neural networks, these neurons processing and all those things we spoke about. The only difference or the only new thing we need to learn as far as trying to theoretically differentiate what a convolutional neural network is as against what a normal neural network is the fact that the structure is a little bit different when it comes to convolutional neural network. So what I'll do is this is a good read from the IBM website where they share some knowledge on convolutional neural network. So I'll share this in the chat and then also in the WhatsApp group so that we can all take time to read maybe after the class. But then there are some few highlights I'd want to point out over here. So yes, basically they start off with telling us what neural networks is all about, and they say it's a subset of machine learning that are the heartbeat of deep learning algorithms. So it says they are comprised of nodes layers containing an input layer, one or more hidden layers, and an output layer. Each node connects to another and has an associated weight and threshold. That's activation. So we've heard about this story over and over again. Now it goes on to tell us what we have over here with convolutional. No, so it says while we primarily focus on feed-forward networks in that article, there are various types of neural networks or neural nets which are used for different use cases and data types. So that point is very important. Most of the time, the problem will kind of determine the appropriate tool that should be applied to. So depending on the data type you are working with, which will then have a ripple effect on the problem. If it is image processing, things of that sort, then our best bet is convolutional neural network because it has a lot of what I'll say um, it has a lot of things that will make image processing much better than any other algorithm we've learned in the past few months. So it says, for example, recurrent neural networks are commonly used for natural language processing, speech recognition, whereas convolutional neural networks are often utilized for classification and computer vision, so image classification, and stuff like that. So, and this is primarily based on the underlying concepts. All of them are basically neural networks. However, it is the structure and the architecture in which we put them that will make a model, what I would say, a convolutional neural network model or a recurrent neural network model. So you see that in a program schedule, as soon as we deal with the convolutional neural network, we then move on to the recurrent neural network, which is the RNN, and then we go on to natural language processing and stuff like that. So at the end of the day, it is the same thing, but it is how we put things in structure that will give us an effective model to perform a particular task. So we cannot finish everything up over here, but then it says, okay, so prior to CNNs, manual time-consuming feature extraction methods were used to identify objects in image. However, convolutional neural network now provides a more scalable approach to image classification and object recognition tasks. Now, leveraging principles from linear algebra, specifically matrix multiplication, to identify patterns within an image. Now, that said, they can be computationally demanding, requiring graphical processing units, that's GPU hardware, to train models. All right. So what we are going to do is, yes, we are going to fall on this and we are going to learn some few things. Now, what we have over here is what we did last year. We have some kind of a template over here. So I'll also share this in the link so that at least you have this template and that's what you are going to work with. So as we always do, we just have to download this over here. And in a matter of seconds, I believe the download will be complete. Now, when we get inside of the files over here, I'm going to explain exactly what we'll be working with and how things are structured over here, because this is going to be a little bit different from what we have been doing in the past few months. So whilst the download, I don't know why it's taking that long, but then whilst we are waiting for the download, let me just give you, okay, have some images in there. So what is happening here is, so in this particular example of convolutional neural network, we are going to build a classifier to classify males and females. So what we have over here, let me just open this up. Okay, I've extracted this. So what we have over here is we have this folder, okay, and then these are templates, how do you call it? Notebook that we are going to work with. But you see that I have this image data over here. When I open this up, I have some kind of a folder, in this case, a subfolder over here. Let me zoom in a little bit. And in here, when I open this up, I also have two folders. So clearly, I have some images, okay, female images and then male images. So when I open this up, these are images of some females I found on the internet. So different images, and they are all females, at least with the ones that we see. Now, clearly, you could also see that, and I'm going to emphasize on this, but then I was trying to be a little bit inclusive, because we don't want a situation where our model is biased towards only Black people or only white people and stuff like that. So you see that in the images I selected, there are some different shades of ladies over here. So for instance, this person is a white lady with blonde hair. We have a white, I believe an Asian with some long black hair. And then there's also maybe a white lady with some different, there's probably a Black woman with a little bit of an afro hair. So we get the point. Different kind of races and stuff like that. So that's what we have over here. And I think there are some few Black people around. So there's a Black woman, there's a Black woman, and stuff like that. So it is fairly balanced in terms of what we all know as women or ladies. Then when we go into the males folder, once again, we have different kinds of males. So for instance, this one is a white male with not too long hair, like short hair. This one also has short hair. Then this one is, I believe, looking at the face like a mixed Asian with bald hair, or maybe a black man. And then this one too, this is typically a black man with short hair. Then we have this one, this, okay. So we get the point. Different images of males. But then one of the things I would want to point out, which later on we are going to come back to, is the fact that of all these images, they are not of the same pixel dimension. Remember, when we worked with the deep neural network, we were working in such a way that we want to resize all our images so that they all conform to a particular pixel dimension, so that when we feed those images in terms of our training to the model, we don't have any problems with dimensionality. So to emphasize on that point, if I'm to do a right click and, for instance, open with paint, you clearly will see that this one, for instance, in terms of pixel dimensionality, it is about 450 by 360 pixel. Okay, there's a pixel dimensionality of this image as we have it over here. Now, the next one, I believe, is going to be different, especially with this one. Even just by looking at it, this almost look like a landscape, and this one is almost like a portrait, something like that. So here too, if I'm to open it up and just do this come to pixel, we get to see that this one is completely different in terms of the pixel dimensionality. So with whatever model that we'll be building, right at the back of we planning how things are going to look like, we are also anticipating that in the real world, when you ask people to send images for classification or anything of that sort, people will come with different images. Some are blurred, some are not too sharp, some are of different dimensionality and stuff like that. Now, what we are doing over here may seem a little bit trivial, okay? But then imagine if this is like, let's say, some breast cancer scans, okay, that probably want to build a machine learning enabled system to kind of classify people, like a breast cancer diagnostic system, basically. So you bring in your breast cancer scanned image, okay, and then we pass it through the algorithm or the model that we built, and then it is able to classify whether you have a problem in terms of having breast cancer or not. So that's the bigger picture I want you to look like. To look at, except that we don't have those images right with us. So at least this is going to give you some kind of a preparatory ground to understand that, okay, once upon a time you worked with some classification model, you use convolutional neural network, and you're able to build a model to classify genders, okay, male and female. So you can extend that to other productive future work one way or the other. All right. Now, one of the things I would also want to point out, so there's a file structure, okay? Now, these are things I deliberately took time to structure. In some cases, the images may be put together. You would have to find your ways to put them in that particular structure so that you don't have problems building your model. So what we are going to do is I'm going to come in here, type in CMD so that we activate this window, and then I'll type in Jupyter Notebook to start the Jupyter Notebook server. So in this process, we are going to build the model, and this is something we've done over and over again, except that we are just introducing a new term, convolutional neural network. At least with a neural network, you already know. So with the convolutional neural network, yes, if you are to open this up, good. So when you do a Google search on convolutional neural network, we are most likely going to see this image, okay? And I'm going to spend time to at least explain some few things as we see over here. Now, the simple or the short note I have over here is a convolutional neural network That's the CNN or the ConvNet, as we saw also in the IBM read. It's a network architecture for deep learning that learns directly from data. Now, in some contexts, the word convolution is simply multiplying of frequencies domain, okay, especially in the context of digital signal processing. So now the objective of this particular meeting, as we are having now, is to build an artificial neural network using the convolutional neural network architecture. Now, we're also going to use this model to classify images. That's a male and female. And then we are going to perform some comparison analysis on some models of the model's parameters. So what I'll probably also ask you to do is, yes, we are going to build this in convolutional neural network, but we can also use the same data set to build one with normal deep neural network. And then we are going to see or try and identify some few things over here. Now, one of the things I also need to mention, which just came to mind, is the fact that one of the interesting things about convolutional neural network is the fact that it was over here. I just want to point it out. Yes. So prior to convolutional neural network, okay, the manual time-consuming feature extraction were used to identify objects in images. So over here, remember with the how do you call it? The previous one we did on Monday, which was the one with the MNIST data set. You realize that we're just let's close it. Hello, Dr. Mills, please, are you speaking to me? All right. So what we did last week, okay, sorry, on Monday, is the fact that these were just single digit images, okay, that we were trying to classify as either 1, 0, or whatever number that was. But then in this particular instance, perhaps maybe there could be an image, okay, and that image, you want to identify a particular object in that image. So maybe there are some cats and dogs, and we want to identify just the cat. Or in a specific instance of, for instance, the breast cancer scenario I just cited, you realize that those who do the diagnosis will tell you that they are always looking out for some specific lamps or some features within the images they analyze. And it is those things that we would want to identify. And a convolutional neural network is going to help us do that, and not just the general framework of neural network just for identification purposes. We can use convolutional neural network to identify objects in images. So there could be a lot of objects in that image, but then convolutional network will rather zoom in whatever thing we are or we train it for to do those identifications. So what we have over here is, for instance, if we have something like this input, okay, probably this is something from the MNIST data set, the way the image looks like. And then we see that this is a 28 by 28 by 1. Okay, so the number of pixels we have over here, which we explained the last time. And then this is just the color channel. Okay, so with the color channel, you see that this is all black. So we just use 1 over here. In a lot of instances, and with especially based on the power of convolutional neural network, we are going to see that it works very well on colored images as well. So in that case, the color channel that we are going to use is going to be 3. And that 3 basically is going to represent the RGB thing we spoke about the last time. So normally what we do is, okay, so for convolutional neural network, we can create a first layer, okay, that's more or less going to be a channel. And over here, we see that we kind of zoom in into these elements pixel by pixel, okay? So we have one channel over here. And for instance, this is a 24 by 24 by some number of n, okay, that we have. And basically, you see that the one we see over here, like I said, this is just a black and white image monochrome. So definitely we have one over here. We are not too much concerned about RGB in here. But then because we are zooming in and convolutional neural network wants to see, even if you are saying that it is black and white, it is still trying to figure out if there are some colors hidden somewhere. It tries to compute some number of channels based on the convolution it does over here. Then it moves on to a pooling layer. Now, with the pooling layer, what it does is, and I think it's a very good example of what the pooling layer does over here. So clearly you could see that with the convolutional layer, let's say we have this, okay, at the very bottom, you see that things have been broken down into some kind of the various parts of the bicycle image or icon we have over here. Now, it tries to kind of break them apart so that for some reason, if it is just this that you want to identify, imagine maybe in the breast cancer data sets or the scans, if you see maybe two big round lumps, it means the person has, for instance, breast cancer. What it means is if it is able to degenerate or decompose the image into something like that, it is able to zone in and specifically look at it and say that, okay, there are two big circles we have over here. So definitely this is, so it is more specific in terms of its analysis. Now we see that with the pooling layer, also known as the downsampling, this one is used to do some dimensionality reduction, because what happens is for every, there's no image over here, but then this one will try and explain that. All right. So for every kind of a metrics inside of that big image, okay, it kinds of filter it, okay. So this one is not giving us a good example, but then this one, for instance, no. Okay, I think there are some images around that we can just look at. So basically what it does is it does some kind of a voting system, okay? So it looks at the particular grade it is zoning in on. And remember, these numbers you see over here are representing, like I said, we spoke about this earlier on, that's metrics representation of the image. Now, it turns out that definitely we are going to have some dominant. Just a minute, Dr. Mills is calling me. Hello, sir.
Really difficult for me to, I don't know, I've just joined again, but it's back and forth, back and forth. If I wanted to do a short presentation on the CNN, so I don't know whether you want to, just to give a brief overview on that. Okay. Okay, all right. Okay. All right, thank you.
Okay, so Dr. Mills has joined us, and he wants to do a brief presentation on the CNN so that I add up to those things. So, Dr. Mills, please, the floor is open for you.
Hello, good afternoon. Sorry, the thing is, my system is strangely misbehaving here. Okay, I wanted to share some quick something on the discussion we were having. You remember that Ken did something with you on the what we call the shallow, the deep multi-layer network. And that deep multi-layer network, it was giving you, we did with the NIST, and the NIST information, we're able to show how we can use that to train data. Now there are two types of deep networks. one of the deep networks is what we have just done now, which is the multi-layer, deep multi-layer neural network. So you can have as many hidden layers as possible. Now, the second deep network that is also used in most applications is what we call the convolutional neural network. And one of the things that we can do is the convolutional neural network. We can do the same thing as is the same thing like as we have been doing what we do in the deep neural. The simple issue that we had with the deep is that the multi-layer neural network is that when we have an image of this size, this image is
I think Dr. Mills just called me, and once again, it appears the network on campus is not looking too good, and I believe that's the reason Derek has also dropped off the line. Okay, and I'm sure others are also trying to join, but then so as and when it gets better, I believe others will join and Dr. Mills can also continue. But then let's proceed to what we were dealing with. So yes, now at the end of the day, we are going to come back to this, and we are definitely going to see how this one will turn out. So obviously these are the how do you call it, the libraries we have been working with over and over again. We are going to work with same libraries, so with some few other additions. So we are going to import pandas. I'm not too sure if you are going to use pandas, but then let's import pandas as PD. Let's import NumPy as NP. Import matplotlib.pyplot as PLT. Let's also import Keras. Import TensorFlow as TF. And then let's run this for the meantime. There are some additional libraries we are going to deal with, and those ones are going to come from I believe Keras and the other ones. Okay, so now that we have that, now let's see how we bring in the data sets. Remember, the data set is already in the folder, okay? Inside of this folder, image data, and then there's a training subfolder, and then we have males and females. So that's what we are going to work with. So in order to import the data, we are going to work with some libraries or some method inside of Keras. So I'm going to say from Keras dot preprocessing processing. I'd want to import a method in there called image. And then once again from Keras, I think sorry, I think my network too has sorry. So let me just continue from where I ended. So over here, I think it is this Okay, so from keras.preprocessing.image, I'd want to import the image, sorry, this one is caps, image data generator. And these two are going to help us work our way through. And I'm having an issue over here. Okay, so I needed to bring imports. Okay, now what these are going to do for us is they are going to help us bring the data set you'll be working with, okay? And it is more or less going to help us. And that's why I said doing this way was intentional, so that we have things properly structured and things are going to work. All right. So what I'm going to do is, let me just come down here and create some new cells. And in these new cells, I'm going to have something like a sample data just for preview purposes. So in this sample data, this image we have over here, we are going to fall on it, and then we are going to call a method in there called load_img. And then in there, we'd want to copy the file path, okay? The file path, remember, it is going to be this big image data, then slash, we go into training, and then we can, for instance, look at the meal. So let's go here, and then let's just copy this one. So I can do a Control-C over here. And then inside of this, I pass it this way. So this is just going to, this is going to help us get at least that folder, but I would want to just work with one single image. So for that single image, let me just use this one, male_1, okay? The names of the images, I just use male_1_2 and stuff like that. So I'm going to do /male_1 dot, I believe, png. The longer it takes, then that means we have a problem. So let me check the file type. Okay, so this is JPEG. So let me just do JPEG over here. So JPG. All right. So this one looks good. So now when I do a preview of this, I get the image I'm bringing down over here. All right. Now we get to see that, okay, this image is now here. We can look at the metrics representation of that image and all those things that we spoke about previously, which we are going to look at it anyway. But I just want to show you that this is something we are going to deal with, okay? And it's going to be from this particular path of the directory that we have created. If for some reason you don't have let's say a training folder or subfolder, you just ignore that. And that's why I just showed you the process of actually getting the file path so that you know exactly where you are working from. Okay, so now that we have this image, let's just skip that process and then move to the next one. Now we just want the whole data set, okay? So the whole data set is going to be equal to this image data generator. And then what we need in here is we want to do a rescaling. The reason why we are doing the rescaling is because of the fact that we have different shapes and sizes of the images and stuff. Like, I want to make sure that everything is conform to one particular format, okay? So this is the first thing we do. And the reshaping or the rescaling we do is we just want to divide everything through by 255. And we know why. Because of the color intensity. It ranges from 0 to 255. So I'll run this and then we are good to go. So let me just coming to the point where we do the analysis of the data sets. So with the analysis of the data set, we have this object over here. I'll just copy this object. And then from this object, I can now, for instance, do this. And there's a method over here. Let me just tap over here. So we want to let the data set flow from directory. Okay, so this one is what we want. So flow from directory, and then we pass in the same directory that we are working with. So let's go back to the directory. This time around, it is the entire data set we want over here, not just the mail side of things. So what I want is the entire data set, which is going to come inside of this. So I'll come and then copy what I have over here. So Control C. So I'll come in here and then paste this over here. So it is inside of this image data folder. I'm going into the training subfolder. In there, I have those subfolders for males and females. I want everything as my data set. So I'll just leave it like this. And now I'm just going to give a target size. So this parameter is going to help us rescale everything to a target size so that we don't have a situation where one image is about this pixel in terms of dimension and another one is about that pixel in terms of dimension. And that's exactly why I had to spend time to show you exactly why we are doing certain things. So with the target size, I'm going to say, for instance, let's say 200 by 200, so that everything is reshaped into that pixel dimension. And then we would want to add other parameters. So for instance, let's do a batch size over here. So batch underscore size. And then for a batch size, let's just say 1 for now. And then the class underscore mode is going to be binary. So a lot of the time, we would want to do this so that the system knows that, okay, based on how things have been structured, it is just some binary classification that we are working with. If it is a multi-class, yes, there are some parameters that will also help us do that multi-class classification. But then in this particular instance, we are just using the binary mode because we only have males and females. So now that we have this, let me just run this, and then we don't seem to have any problem. But then we get something interesting printing out over here. And it tells us that, well, after putting in this file path, okay, calling this method from this object that we have created out of this image data generator, okay, it is telling us that, well, it found 34 images belonging to 2 classes. And this kind of makes sense because indeed, if I'm to come in here and go into the female class, I have 18 images over here. And then if I'm to go into the male class, I also have 18 images. So definitely I have those number of images, that's 34, belonging to 2 classes, that's a male and female. So this gives us a very good indication of whatever thing we have inside of our data sets in terms of the images that we have. So if there's about 1,000 or hundreds of millions of images, we don't really have to do the counting. This is going to help us get an idea of how things are beginning to take shape like. Now, there are some few things we can look at, okay, which is also going to help us. So this data set that we have created, this object, if I'm to now do a data set dot, I think there's one called class indices. So when I print this out, it tells me that based on the structure I have over here and the name of the folder I gave and all those things, it is going to see all females or all things belonging to the female class, or all images belonging to the female class as 0, and then all images belonging to the male class as 1. Okay, it kind of makes sense over here based on some of the things we've done. But then what actually happens in terms of determining which one becomes 0 and which one becomes 1 is that it basically looks at how do you call it, the names of the folder that you have, okay, and then based on alphabetical order, F comes before M. So basically, the folder that comes first is going to be assigned the first index in terms of Python indexing. We know the counting starts from 0, and then it goes on. If it is a multi-class, then it will go on. If we had, for instance, a class called animals, okay, then the animals is rather going to assume the the 0th index or the first index position, and it goes on and on. Okay, so these are things we cannot worry so much about. Now let's do another one where we can do data sets dot, I believe, classes. And this is also giving us some information I think we should be comfortable with, because if you look at this, you see that the first 18 we have over here, based on what we know from this, the class indices, is that, okay, all these are females, because when we go into our data, okay, and we go into, for instance, this is the 0 and this is a 1, based on the indexing and how things have been structured. When we come in here, all the first 18 are all 00s in terms of their class. They all belong to class 0, which is a female class. And then the last 18 also belongs to the 11111. And that's simply because of the fact that the other one is what we see over here, which all belongs to the male class, or the class of index position 1. So at least this makes a lot of sense. Now let's look at something interesting, because this is going to help us appreciate why we need this pre-processing to help us work. Now, if I'm to do the data sets dot, for instance, the image shape, as I have over here, it now tells me that, well, for all the images you have, it is a 200 by 200 by, this is a color channel, because this, I mean, all the images we see over here are so much colored, okay? So there's some color combination of RGB colors we have over here. Now, this is very important, because initially you realize that this one, for instance, the pixel dimensionality we saw over here was 1000, approximately 1000 by 800, okay? Other ones will probably be less. This one, for instance, is going to be something not compared to this one, is also 1000 by 1250. So you get the point. But based on what we've done so far, we've come to a point where we've rather resized and reshaped everything into some kind of a standardized 200 by 200, and the canal channel is what we have over here. Now, this also means that if at the end of the day, after building this model, I want to test it with our own images and stuff like that, we also need to kind of do a reshaping of whatever image that we are going to have into this in order for this to work. All right, but that is something very simple that we are actually going to do. So now that we have this and things are looking good, we can actually go to the point where we build a model, okay? Because our data set is clean over here, we don't have any problem. Now let's go and build the model. So we get to the point where you are building the CNN model. Now, once again, I'm going to say from Keras dot models, I'm going to import sequential. Then the layers is where the magic comes in. Okay, so remember, in the case of the which one did we look at the other time? In the case of the image processing, okay, initially we were just working with the dense layers. Then we came to a realization that no, sometimes you also need a flattened layer, so that it flatten things up for us to be able to feed those matrices into the network. Good. So it is the layers that most of the time changes. So I'm also going to say from keras.layers, I want to import, and we still need a dense one way or the other, okay? And then there are some new layers that we need, okay? So we also need a flatten, because we've dealt with this flatten layer before. And then because we are working with convolutional neural network, we need the conv 2D. This is something which is already given to us, okay? Then we also need the max pool 2D layer. And that's what is going to constitute some kind of these images that we see over here, okay? There's going to be some max pooling, and there's going to be some, how do you call it? The general architecture of the convolutional neural network, basically. So we have this ongoing. Now let's continue to actually build the model. So the model that we are going to build is going to be, first of all, this kind of a sequential model because it moves in that sequential order, okay? Then the layers are what we are going to put in things to make sure that things are in that convolutional neural network architecture. So for that to happen, let's come down here. Now I'm going to do model.add. We are going to add one layer, or the first layer. And the first layer we are going to have is the 2D, because we are building a convolutional neural network. And then remember what we see over here, especially with the image, you see we are trying to put up the architecture, okay? Now, as far as whichever dimensionality we put up over here, it's a matter of choice. However, we don't want to make things overly convoluted, if that makes sense. Okay, we don't want to, because at the end of the day, the whole concept of convolution is trying to split things and then do some multiplication of things. All right, now because we are, for instance, this one, for instance, moved from a 28 by 28 by 1 to a 24 by 24 by some number of n channels. Okay, so maybe 3. Now what this one basically meant was, okay, we kind of shrink this, okay, a little bit. And what that shrinking from 28 to 24 basically means that, well, we probably want to get rid of some, for instance, some particular pixel, okay? So maybe counting from 0, 1, 2, 3 up to this point probably is a 24, which definitely is not going to affect our work so much, because at the end of the day, the image is somehow centered in the middle. So that kind of works in a way. But then if we are to choose some kind of the dimensionality over here, where maybe we are dealing with 5 by 5 or something like that, then probably things may not work out properly, okay? But with this particular one and what I've built and what seemed to work, we are going to put up the channels at 16, okay? And then inside of this, we have a 3 by 3 over here. Then we specify an activation layer or activation function. Now, what we are going to do over here is, at the end of the day, we are going to build two models of the same kind, okay? They are all going to be convolutional neural network models. And then we are going to do some comparison based on something I think I've spoke about, and I believe the other day, I remember maybe it was Mariama asked the question in relation to that. So maybe this one also reinforced the explanations I gave some time ago. So for our activation function, so activation, we are going to use ReLU. These are things we've done in the past, so we understand this. And then for the input shape, remember, we are still dealing with the input shape over here. For the input shape, what I want to do is, okay, for the input shape, what really do I want? This is actually going to be the input shape, because this is going to be a 200 by 200 by 3. So what I can do is I can actually come and copy this instead of just hard coding it, because that's essentially what we specified over here for our target, okay? So I can copy this one and say the input shape is going to be exactly this. That's another way of basically typing, how do you call it? 200 by 200 by 3. So that's going to be the input shape we are specifying over here. And let me just check if everything is accurate over here. So we have the conv2d, and then we have the 3 by 3 activation function is ReLU, and then our input shape is looking good over here. Right. We are having too many. Okay, let me just. Okay, all right. Now let's move on to the next layer. The next layer is going to be based on the structure we have over here. Is we are going to go into a max pooling layer. So what I have is the model.add. And the reason why I'm bringing this up is, once again, when you spend time to read what I have over here, you are going to understand why. Let me just quickly do this. Good. So when it comes to the pooling, like I said, we are using the pooling to reduce dimensionality, okay? And the point is, if you are reducing dimensionality, then it means we are kind of going to also reduce the quality, because the dimensionality basically has a ripple effect on the quality of image that we have. If we have 1,000 by 1,000 pixel image and we are reducing it to, let's say, a 200 by 200 pixel image, definitely the quality will go down. However, with those quality going down, we still want to make sure that we retain the most relevant features that makes that image that image. So for instance, we are seeing that, well, the pooling layer, also known as the downsampling, conducts dimensionality reduction, reducing the number of parameters in the input, similar to the convolutional layer. Now, the pooling layer operation sweeps a filter across the entire input, but the difference is that this filter does not have any weight. Instead, the kernel applies an aggregation function to the value within the receptive field, populating the output array. Now, there are two main types, and the first one you have is the max pooling, and then the other one is the average pooling. And I'm going to see if I can get an example to explain this briefly, because this one is very important for us to make progress. There's usually one image I've seen a lot that others have used for this explanation. Let me just quickly go to images and good. So you see that, let's just concentrate on this. So with the max pooling, it looks at every kind of a grade, okay? So over here, we have this grade, we have this grade. So let's say 4 grade. And it kind of, this is doing a 2x2 max pooling. So what it does is, it looks at this particular grade. What is the highest value over here? Because that's the maximum pooling. It says that, okay, for this, it is 20. So it pulls 20 over here. Now over here, looks at the maximum, it is 30, it pulls 30 over here. Over here, looks at the maximum, it is 112, it pulls 112 over here. And over here too, the maximum is 37. That's why you see 37 over. And you can also do a comparison with the other examples you see over here. Now, basically, what is happening is, based on our understanding of images and what these numbers means, okay, these numbers are some RGB, and the point is, the higher the number, that means the higher the intensity, or maybe how deep that color is. So the point is, yes, we are interested in all the colors we have over here, but then 20 means the color is very deep. So it is probably of more significance than maybe this one. Okay, the 30 is of more significance than the 0 in terms of the color, in terms of we trying to identify a particular object in there. Because if we end up working with this whole big matrix, then we come back to the point where it says, we come back to the point where it says that I think earlier on, good. It says that is it that, however, convolutional neural network now provide a more scalable approach to image classification and object recognition tasks, leveraging principles from linear algebra, specifically matrix multiplication, to identify patterns within an image. That said, they can be computationally demanding, requiring graphical to train models. So yes, normally images, because of the big matrices we have in there and some calculations, matrix multiplication, when we do the max pooling as we are currently handling this way, it kind of take out the relevant or the maximum data point we have over here, which is basically going to represent some color one way or the other, into a new matrix that is going to be a little bit more detailed than just this big one. So when we come back here, that's exactly what we are trying to illustrate here. That's whenever we do the max pooling, it kind of shrinks the image a little bit. However, the shrinking is done, but we maintain the most relevant, because we are looking at the maximum values out of those metrics that we have in there. All right. So let's just move on. So for instance, let me just give maybe some illustrations for us to understand. So let's assume, okay, because of max pooling, this image has been, let me see if I can get a different color. Good. So let's say this one was divided into, let's say, 4 this way, just for argument purposes, okay? Now, and let's say this one is subdivided, okay? This one too is kind of subdivided, and it goes on and on. This one too. Just for us to understand this, okay, in terms of maybe color, this is a little bit whitish, okay, getting to 0. So maybe there's a 1. This because of maybe some other black and other things. So maybe this is probably the 20 that we saw over there, okay? And this is probably maybe another 1, and this is not too thick as compared to this. So maybe this is a 15. Now, in terms of max pooling, it is going to pick up this quadrant, okay? And probably when it is shrinking, it is going to shrink off these ones off because they are not carrying some kind of relevant data that's going to help us in our classification. And this particular one makes a lot of sense. Okay, other ones maybe I may find it very difficult trying to explain that, but then this one makes a lot of sense because indeed, what makes this image so unique does not lie in the kind of things we see over here, but then it is the kind of things we see probably over here, because over here you can see that we have the eye, the hair, and other things, and those are the ones convolutional neural network wants to concentrate on, other than what we have over here. Else, it is going to be computationally expensive, going to run a lot of matrices, because all these things we see over here are going to be some numbers one way or the other. So this is just to help you get that general concept of why we are using the max pooling and the work it will do for us. So you could clearly see that this is much detailed, okay, in terms of how it operates than the deep neural network we built the other day. And that's where we can actually use this to actually identify a particular maybe object in an image. So we have this max pooling, and then let's see what we have. So we have max pooling, and with the max pooling, let me just bring max pool. So max pool 2D, and over here you just specify this as 2 by 2. Okay, we can change the parameters later, but then let's just look at this. Now, I'm also going to add another layer. So I'll do model.add, and this time around, I would also want to add in a convolutional layer. So let me just copy this and change some few things as we move along. So yes, remember, I'm not bringing the input shape because I've already dealt with that, okay? So over here, the only thing I need is an activation function to do the calculation for me. All right. Now, the layer I want over here is probably, let's put in a 64 just to make things a little bit more convoluted. And then we come in here, we do another max pooling. So we are still maintaining the ReLU or the rectilinear activation function. And then for the max pool, I'm also going to maintain this over here. And then pretty much now it is almost like alternating between the convolutional neural network layer and then the max pooling layer to make sure that you have a good convolutional neural network. Now, as far as the activation function goes, this is where it gets a little bit tricky, and I'm going to show you what we are going to do, especially for those two models that we are going to work with. So over here, once again, let me just change the parameters. I think I'll go with 32 over here. I'll maintain the 3 by 3. I'll go with ReLU. Then I'll do another max pool. And then finally, let me come in here and do another convolutional network. Or maybe it's enough for the way I'm bringing things up over here. I've even forgotten how computationally expensive this can be. But then after everything is said and done, so let me just end in here. So after everything is said and done, okay, we're doing the max pooling, bringing the convolutional network layer and stuff like that. At the end of the day, we need to flatten things. Okay, we need to flatten things up over here, and we saw what the flatten does for us, especially the way we want things to work. So I'll do model dot that flatten layer we brought up over here. So this is going to flatten things, and at the end of the day, look at the image we have over here. At the end of the day, we feed everything now into the some kind of a neural network, okay, a fully connected neural network. Now what is happening here is, okay, are we actually doing calculations and stuff like that? Remember the point that we read over here, that good, the convolutional layer. Now this is the core, okay, building block in CNN. Now it is where majority of the computation occurs. Now it requires few computation where the input data and um, a filter and a feature map. Okay. Now let's assume that the input will be the color image, which is made up of a matrix of pixels in 3D. Now this means that the input will have 3 dimensions. Okay, the height, the width, and the depth. Sorry, the width and the depth. Now, which correspond to the RGB in an image. This we've come to understand in the previous weeks. Now, we also have a feature detector, also known as a kernel. We know what kernels are, which also will move across each one. Now, the feature detector, I was trying to look for something. I think I read it earlier on. But basically, what is happening is when we have additional layer. Okay, now the name of the fully connected layer aptly describes itself. Now, as mentioned earlier, the pixel value of the input layer are not directly connected to the output layer, partially in a partially connected layer. However, in a fully connected, oh, I saw something is becoming a little bit too many. But then basically, let's go back to the image we are relying on over here. Now, after everything is flattened, basically what this is actually doing for us is when we are doing the convolutional layer and the max pooling and the convolutional layer and the max pooling, as we have written the code for, it is basically trying to find means and way to shrink the image down such that we only concentrate on the most relevant features in there. And those most relevant features now is now flattened and fed, or is going to be fed into a network. That's basically what we are doing with that convolutional neural network. So we do the convolutional things over here to get the most relevant ones, and then we flatten that, and then we feed this into a dense layered network. So I'm going to do model.add. I think I should add and then flatten this way. So we are going to do model.add, and then we are going to pass in a dense layered network, and then let's say I pass in 200 neurons. Now for 200 neurons, I'm going to put in an activation function of, let's do relu over here. And finally, let's come to our output layer. Remember, this is a binary classification. Okay, so for binary classification, what we can do, and what I'm going to do is I'm going to do model.add, and over here too, I'll need a dense layer, and I'll just pass in 1 neuron because this is a binary. But then the activation I'm going to use over here is going to be sigmoid. And by now we should understand why we are using a sigmoid activation function over here, because we are just dealing with one layer for the output and we are expecting either a 0 or a 1. So remember, when we draw the sigmoid graph, the output is either going to be a 0 or a 1. All right, so I think this can work. We have some few issues over here. It says invalid syntax. It was perhaps expecting a comma on line 8. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. Is that it? No, it is convolutional 64 33 relu. Model.add conv2d. This is the first instance of it. So model.add conv2d, comma 3x3, comma activation. Oh, okay. It's supposed to have another bracket, because this first bracket, okay, is for this one, and then this second bracket for the convolutional should encapsulate this. So I think these brackets are missing. Okay, so I think this one should work. And then we have an issue. It says the max pool is not defined. So I think there's a typo over here. It is supposed to be pool. Sorry for the interruption. I think my network dropped. So let me quickly go back. So it is a max pool 2D. So these are some typos we have over here. Okay, so I think this one should work. So a model has been built, and now it's time to fit or to compile the model. All right, these are things we've done. Okay, these are things we've done looking at the previous examples that we work with. So I can do model.compile, and then I'll bring in an optimizer over here. We are using Adam as we usually use, and now the loss function we are going to use is the binary cross entropy. So binary underscore cross entropy, and then the metrics we would want to monitor is going to be the accuracy. All right, so we can compile our model at this point, and bear in mind the other model that we are going to build, okay, which is just going to, we are just going to copy and paste and change some few parameters. We are going to look at an instance where the last activation function we use for our final layer over here is not going to. Sorry once again. Okay, so now let's go to the point where we actually fit the model, because we've done this before. So I'm going to do model.fit, and remember we already have our data set, okay, which is this data set we know. So let's pass in data set over here, and then we specify the epoch, and for this one let's just do 10, and let's run this model. And then okay, so as it stands, we don't have any problem. It started off with an accuracy of about 47%. It moved to 60, now 70. And then I think we are doing much better over here, 80. The fourth iteration, we are about 90 over here. So it is looking good. So it has gotten to a point where it's telling us that, well, it is 100%